Log on, tune in, find out. Another good idea from Cambridge.
Welcome back. So now it's my pleasure to introduce Ken Brown from Glasgow, who will tell us about Hopf algebras of small Gelfand-Kirillov dimension.
Thanks very much. It's very nice to be here. So, plan, I suppose. So a little bit of background then. It's a very simple idea, this talk. I tell you some examples of some Hopf algebras, and then hopefully the theorem would be those are the only ones. Unfortunately, can't quite prove that. So can kind of partially prove it. So there's a conjecture and a theorem, and then a little bit of proof hints. Okay. So for the background, I'll just tell you one or two things about one or two of the words in the title in particular, in case not everybody knows Gelfand-Kirillov dimension to start. Is measure. It's just really for us. It's I'm not going to use anything at all sophisticated about Gelfand-Kirillov dimension. It's just a convenient measure of size, smallness, in effect. But anyway, here's the definition. So we start with an affine K-algebra. Affine just means finitely generated as an algebra. So let's say K is a field. So we have, say, D generators. And let's set A naught to be K. I'm going to build an ascending filtration indexed by the non-negative integers. So A1 be that. And then inductively we just define A2 to be the subspace spanned by all products of two elements of A1 and so on. Like that. And then the Gelfand-Kirillov dimension of A is the smallest mu such that the dimension, vector space dimension of A sub n is bounded above by n to the mu for big enough n, or infinity if there's no such mu. Okay, so there's some obvious trivial things that one checks. It's independent of the way we build a finite filtration like so. Takes values in well, it's pretty easy, 3 or 4 lines to see that it can't take any values strictly between 0 and 1. It's a theorem of Bergmann's from, I think, the mid-70s that it doesn't take any values between 1 and 2, but then it can be any real number. Whoops. Bigger than 2, including infinity. But, which sounds kind of bad, really, but for reasonable algebras, it's in non-negative integers, union infinity. Although it's not so hard to construct these examples with real number of values, half a page, really, just a very clever idea. Okay. It generalizes our standard idea of the dimension of an affine algebraic variety. So, just to record that, if A is an affine commutative domain, say A is the functions on the variety V, then the Gelfand-Kirillov dimension of the ring A, the algebra A, is just the dimension of the variety. So it's a sensible gadget to generalize our geometric notion of variety. So the word small in the title basically means very small. So small will be 0, 1, or actually maybe could be 2. 0, you can see from the definition, if and only if A is a finite dimensional algebra. 1, on the other hand, there's a nice classic theorem about algebras of Gelfand-Kirillov dimension 1, which is due to Small, Stafford, and Warfield. So suppose A is an affine semi-prime, so no non-zero, no potent ideals. Of Gelfand-Kirillov dimension 1. Then A is not far from being commutative. So it's a finitely generated module over its center. And of course, its center, Gelfand-Kirillov dimension is well behaved with respect to taking subalgebras, as you would immediately realize from the definition. And so the center is, the Artin-Tate lemma tells you that the center is itself an affine, commutative. Should better have a field floating around. So the center is an affine algebra of GK dimension 1. So if we actually had assumed a prime here, so rather than semi-prime, so product of two non-zero ideals always non-zero, then the center then would be a domain and would be the coordinate ring of a curve. Yeah.
About the reverse direction, also drop.
If you take these assumptions on Z, yes, but that's much easier. Yeah. Yeah. Okay, so that's enough on Gelfand-Kirillov dimension. On Hopf algebra, I'm going to assume this being the audience it is, that everybody knows what a Hopf algebra is, but I will fix some notation. So most of the time my Hopf algebras I'll call H. So as you know, there's various bits of baggage that a Hopf algebra carries around. A coproduct, which is a map, I'll call it delta. From H to H tends to H, and I'll use some variant of the Sweedler notation for that. So we'll write the image of little h as sigma H1 tensor H2, and this is by definition an algebra homomorphism. So as will happen later on, I want to tell you what various coproducts are. I only need to tell you them on the generators, tell you what delta is on the generators, and you know what it is for everything. Co-unit, similarly an algebra homomorphism, this time from H to the ground field, and the antipode, finally, which is a map from H to itself, and it's an algebra anti-homomorphism. So S of x times y is sy times sx. And then these things have to satisfy a bunch of axioms, which I won't list. Okay. So the idea is to understand or classify small affine Hopf algebras over a field. And we're going to have to impose various extra hypotheses along the way. The first is to avoid having the subtask of classifying all finite dimensional Hopf algebras. So in order to avoid doing that, the easiest way is to assume that H is prime, which as already said means product of two non-zero ideals is always non-zero. Because if H is prime and finite dimensional Hopf algebra, well, it always has any Hopf algebra always has a two-sided ideal of vector space codimension 1, namely the kernel of the co-unit here. So if you, in addition, assume that it's prime, then it's rather easy. It's just the field. So we can duck out of having to understand all finite dimensional Hopf algebras by assuming prime. So our aim, if you like, is to classify all prime affine Hopf K algebras of G K dimension equal to 1. Right. The aim is not achieved, as I've already kind of indicated. And the non-achievement is still attained, despite imposing some extra hypotheses along the way, first of which is going to be on K here. I'm going to assume that K is always algebraically closed and that its characteristic is 0. And just in case I forget to say later on, these conditions are both needed for the theorem and conjecture that come later. So I should mention that this is joint work with James Zhang of University of Washington. And there's a preprint on archive. Okay, examples. So that's section 1. Section 2. So here H will be as in A. Okay, and let's see what things we can come up with. So first of all, if we assume H is commutative, so then, as everybody knows, there's a equivalence of categories between commutative, affine, Hopf algebras, which are domains, and connected algebraic groups over the field. So if we assume, as we are assuming in the aim, dimension 1, there are only 2 possibilities. So H equals O of G for some G of dimension 1. And let's make a list over here. So the group could be the one-dimensional torus, which means that H is a Laurent polynomial ring. Let's just give you some ingredients. Delta sends x to x tensor x, and the co-unit sends x to 1. Oh, antipode, why not? Or we have the affine line. So this time the co-product sends x to x tensor 1 plus 1 tensor x. And that's what S and epsilon do. It's worth writing these down, even though probably most people know them extremely well, because as you'll see shortly, the non-commutative examples are somehow built on top of one or other, on possibly both of these prototypical examples. So suppose now we drop commutative, but retain, if you look at these co-products here and here, they both are symmetric. And the Hopf algebra jargon for that they're invariant under the flip, is that the Hopf algebra is co-commutative. So supposing that we now drop commutative, but keep co-commutative. So there's a really classic theorem this time from I guess the late 60s, which is very, very dodgy to write down attributions of any theorem in this room, I seem to have found, but especially of these really classic theorems. So I'm going to play safe here by writing 3 names, and you can permute your preferred order and subset. So the Cartier-Gabriel constant theorem says basically that any co-commutative Hopf algebra over an algebraically closed field, affine, is built from a group algebra acting on an enveloping algebra. When you've got dimension 1, there's not much room for maneuver here. So what about group algebra? Well, we've already got one group algebra on the board. There's another one which is non-commutative, but only very slightly non-commutative. That's the group algebra of the dihedral group. And because it's a group algebra, the group elements are group-like, which means that the coproduct looks like this. So delta of A is A tensor A, and delta of B is B tensor B. Co-unit sends group elements to 1, and the antipode sends group elements to their inverses. That's not the only co-commutative but not commutative case. We have things that I'm going to call the co-commutative Taft algebras. So I'm calling them that, although I'm not really sure that Taft ever wrote them down in this way, but anyway. So Taft constructed some examples in the mid-70s, which in some sense included these. So for this we need n, an integer greater than 1, and psi primitive nth root of 1. In our base field. And getting a bit tight in here. So I'm going to use what looks extremely perverse notation, n0 psi. Which will become, the reason for which will become apparent in a minute or two. So we have two generators here, x and g, and relations. Better get my order of twisting consistent. Okay. So xg is psi gx, and g to the nth is 1. And delta does the obvious thing, so x is primitive here. X goes to x tensor 1 plus 1 tensor x. G goes to g tensor g. Right, and that's all the co-commutative examples. So now, let's see. Okay, so we can first of all doctor these Taft examples a little bit. So we keep n and psi as above, and take t in Z between yeah, T1 and N. And then what we do is we keep the same algebra here, but we change the coalgebra structure. So we replace 0 by T, and in here I replace a 1 there by G to the T. So you immediately recognize this, I'm sure most people in the room, as a kind of, well, for a certain choice of T, it's a factor of the Borel and UQ-SL2. But you know, you have a fair degree of flexibility with T. And when James and I started doing this game, we kind of thought maybe that's all the examples. And we were sort of started out on the route to proving that when we got a preprint from somebody, some unknown person, unknown to us, in China, mainland China, called Liu. And so this class of examples we're calling Liu algebras, class of examples that he described in his preprint. In fact, it turned out in the proof of our theorem, we found he hadn't got them all somehow. You need to enlarge the ones he constructed a bit. So let's call them generalized Liu examples. So they're quite pretty. If you like algebras with nice generators and relations, then I think they're pretty, these things. So we need the same n and psi as above. By the way, I mean, another thing to remark, just before we look at these Liu ones, you can realize that everything, as I said when we did the commutative ones, everything else on this list so far is some kind of n-fold cover of these, where in the case of the dihedral group, it's a two-fold cover of the one torus. And here you've got an n-fold cover of the affine line with the Taft algebras. And that pattern continues here with these Liu algebras. So n psi as above, and then take another integer greater than or equal to 1, w. I need some notation, I'm afraid. Greatest common divisor of n and w, let's call that b, and I want to make it positive. And then let's write factorizations of n and w as n dash b and w dash b. Okay. Yeah, I think my list is not going to fit on that board, so I'll avoid saying anything about margins. Let's put it here. And let's use L in honor of Liu. So NW psi. So the idea is that we build a cover of a Laurent polynomial ring or of the torus, if you like. But there's an extra piece. We can throw in a finite group on the bottom as well. And then the acting element I'm going to call Y. So H and F generate a group, or over K, a group algebra. So I have F to the B is 1, and HF equals FH. And Y, psi commutes with H and F, so to be specific, YH will be psi HY and YF. So it has to commute with some bth root of 1 because F is order B. So I take psi to the n dashed. Okay, and then y to the n. So now if I just made y to the n 0, you could imagine, I'm not going to do that, but if you imagine I did that, I'd get a Hopf algebra. I could impose a Hopf algebra structure on this, but it wouldn't be prime. In fact, it wouldn't even be semi-prime because y here, because of these skew commutation relations, y generates the one-sided ideal generated by y is two-sided, and if y to the n was 0, I'd get a nilpotent ideal, which is not what I want. I want prime algebra. But the nice thing is you can twist around the relation and make y to the n equal to something in your group algebra if you choose it carefully without messing things up. So we take y to the n to be 1 minus h to the n w dashed. And then delta, so h and f are group-like. So we just get the group algebra. And then y is a skew primitive element. So y goes to y tensor g plus 1 tensor y, where g is some carefully chosen element. Which I'm not going to tell you about. You can look it up if you care. Of the subgroup generated by H and F. Okay, so it's some sort of n-fold cover of this, which is the torus, and it satisfies all the conditions on the aim, wherever it's gone here. Okay, so what should come now in a perfect world would be a theorem. But that's not the case. So take H and affine prime Hopf K algebra. So first of all, I need an extra condition before the conjecture, even never mind the theorem. So the conditions are, and the proof for that matter, are now require some homological ingredient. If you think about algebraic groups for a minute, of course, these commutative Hopf algebras are all smooth. Basically because you can move from one point in the spectrum to another by the regular representation. So every maximal ideal looks the same, so the locus of smooth points must be the whole space. That's not true for non-commutative Hopf algebras in general, even prime ones, even domains, even GK dimension 1. And so, well, even prime GK dimension 1. And so, in order to get a theorem, in other words, in order to exclude some possibly large further set of counterexamples, I've got to assume smoothness. So suppose that H has finite global dimension. Then, so conjecture first. So all the ones on the list satisfy these hypotheses, and conjecturally that's them all. Well, the extra condition we need to prove the theorem is that the pi degree, polynomial identity degree of H, is a prime number. I'll tell you what pi degree is now. In fact, I'll give you 3 equivalent definitions. So this guy is prime. Remember from the small Stafford-Warfield theorem there on the board, it's a finite module over its center. Center is a domain, so we can invert the center and we get a field, and then we can measure the vector space dimension of the quotient ring of H, which is a simple Artinian ring. Matrices over a division ring. We can measure the dimension of that over the center of that simple Artinian ring, which is the quotient field of the center of H. It's always a square by the theory of central simple algebras. And the pi degree by definition is the square root of it. And it's also equal to the maximal k dimension of simple H module, and it's also equal to the generic dimension of simple H modules. So for these guys on the board, the pi degree obviously 1. So pi degree is 1 if and only if the ring's commutative. So you get 1, 1, 2, n, and then you get the feeling by now. The Lie ones are pi degree n. So if n is prime, then that's the list. If n's not prime, then we believe it's the list, but we can't prove it. So I tell you a bit about the proof, just mainly so you get a feeling for where this condition comes in, and also to, well, I think the proof is at least as interesting as the theorem, actually. So, yeah, sure.
The global dimension.
The global dimension is the projective, the supremum of the projective dimensions of the modules. Do you want me to say a bit more, or is that enough?
Right, enough, yeah.
I'll say a bit more. So for every module, you can take a projective resolution, and it's the minimal length of that such projective resolutions gives you the projective dimension of that module, and then you take the supremum over all modules for your ring. So for a variety, an affine algebraic variety, it's smooth in the geometric sense if and only if the global dimension is finite. That's a theorem of Serre, I think. And when it is finite, it's equal to the dimension of the variety. Okay, any other questions? So actually that question is kind of opposite right now, because the key to getting started on proving the theorem is homological. So if you think about, so what's the structure of the proof? The structure of the proof is you take an algebra that satisfies all the conditions in the theorem, and then you hack at it for a long time to try to prove that it's one of the guys you have on your list. Okay, so somehow if you look at the list, you realize, what ingredients do I need given H as in aim, let's say. We need two things. We need a copy of kx, or kx plus or minus 1, somehow nicely embedded inside our algebra. And this some sort of automorphism of finite order acting somehow intrinsically in the structure. In ignoring the commutative cases where the finite order is 1, here it's order 2 in the dihedral, and here in the Louis and Taft guys it's n. So we need a group of autos of H of order n. You've got to concoct that from somewhere. And the source for, we start with the second thing, and the source for that is homological algebra. Because, and the point is that although these non-commutative, non-co-commutative Hopf algebras are not smooth in general, unlike the commutative case, they are homologically appear to be very nice. So let me tell you a little bit of history. If you think for a moment of a finite dimensional Hopf algebra, for instance, group algebra of a finite group. So it's another classical theorem that these are all Frobenius algebras. This is due to Larsen and Sweedler. So homologically speaking, Frobenius, being a Frobenius algebra means injective dimension of H as a module over itself, say as a left module, also as a right module, is 0. So injective dimension is the dual of projective dimension. We take our module and then we take its injective hull, take the injective hull of that, build an injective resolution, and it's the least smallest length of such a thing where all the terms are injective after the starting point. And injective dimension 0 means H itself is injective. So this is kind of homological niceness condition. How should it generalize if we drop finite dimensional? So I have a conjecture which is now well over a decade old and still open, which says that every Noetherian Hopf algebra has not injective dimension 0, because injective dimension 0 basically implies finite dimensional, at least if you're countable dimension to start with, but finite injective dimension. And in fact, so every known Noetherian Hopf algebra, all the obvious ones, enveloping algebras, quantum groups, quantized function algebras, they all satisfy this conjecture. In fact, the conjecture, I'm not going to go into details, but the conjecture says that they should have finite injective dimension in a very nice way, that they should have some kind of sexy version of finite injective dimension, which is called Artin Shelter Gorenstein. So in fact, H should be so that's usually in the literature shortened to AS. So AS Gorenstein stands for Artin Shelter Gorenstein. And what it means is, very, very briefly, is if we take the X groups, so if we're looking at the injective dimension of H, we should put it in the right-hand argument. And because it's a Hopf algebra, one of the things about Hopf algebras, as you know if you study quantum groups or enveloping algebras or groups, is that the most crucial module is the trivial module, the one realized by the co-unit. So you put that guy in there. And Artin Shelter Gorenstein says that this is almost always 0. It's not 0 at one place, so that's Kronecker delta ID. And when it is non-zero, you just get a copy of the field. And D here is the injective dimension of H. And should equal, part of this Artin Shelter Gorenstein shtick is that it should equal the size of the algebra as well. So this is with there's a white lie in here because H might not have finite GK dimension, but if it does, then it's likely to equal this. Okay, so how does this have any bearing on getting a group of automorphisms of order n? Well, the point is, look at this X group here. It's as trivial as you can get, you might say. Let's look at the Dth one. I should say, this conjecture is true in our world of GK dimension 1 Hopf algebras. conjecture holds for all, in fact, for all H which are finitely generated modules over their center. This is a theorem from 2002 of Wu and Zhang. So I can home in on this guy for now. If I take H as in the theorem, as in the aim, then the D is 1, the crucial D. So I'm looking at X1 here, and it's K. So it's a one-dimensional vector space, but it has extra structure because this isn't just a vector space, it's a module over the Hopf algebra. And it's a module in two ways. It's a left module in a boring way via the right action on. So I'm thinking here of building my X group using left modules to start with. But both the arguments are, of course, bimodules, so I still have two free places to act. So the left structure here is trivial. I just get left trivial, so killed by the augmentation ideal, in other words. But I also have a right structure here. So I get a one-dimensional H module on the right, which may or may not be trivial. Sometimes is, sometimes isn't. So let's call it something. Since it's a one-dimensional module, I can think of it if I want it. I can think of it as a character, so let's call it chi. Call the right structure chi. Okay, so I mean, if I want, I'm going to think of that as an algebra hom to k, which might be the trivial, might be the co-unit, but it might not be, and sometimes it's not. So whenever I have in a Hopf algebra an algebra homomorphism to the base field like this, I can use it to construct what's called winding automorphism of H. As follows. And I'm going to call this tau sub chi. Which sends H so this here is I'm using the Sweedler notation from way back at the beginning. H gets sent by the co-multiplication to sigma H1 tensor H2. And then I apply chi to my right-hand arguments in the tensor product to get some field elements. Okay, and then I bring them up, get rid of the tensor product sign by multiplying. And that's an algebra automorphism. Notice I chose right here. That was a choice, so I better label it tau r. I could also do the same on the other side. And if H was co-commutative, so if the co-product was symmetric, then these guys are the same. But if H is not co-commutative, they usually won't be the same. You get two different algebra autos of H concocted out of this one-dimensional module. And so then I get two groups of automorphisms. I get, let's say, GL. The subgroup of the algebra automorphisms of H generated by tau L, and similarly GR. Then it's a proposition. That always, if H is finite over its center, not too far from being commutative, these automorphisms, although not in general trivial, always have finite order. So, I mean, the order is the same. Okay, so I get that. And then I define the integral minor of H to be, to measure how different they are. So the index of the intersection in one of them or the other of them. So it turns out, let me just finish by speaking now. It turns out that this integer n is the integer n that comes into the theorem. Okay? This index, the integral minor, is 1 not only if H is co-commutative, so that tau r equals tau L, but only if. So this is measuring how far away H is from being co-commutative. And basically, the reason why the condition about n being prime comes into the theorem is that we can prove the theorem in two cases. One is where GL equals GR, and so this number is 1, and the other is where GR intersect GL is 1. And so we get the intersection being just the identity. And of course, if n is p, Lagrange says, that's all that's possible. But in general, well, probably it's just technicalities, vast technicalities, but we can't handle them at the moment. So that's all I wanted to tell you about. Thanks very much.
Questions?
Look at all of the modular case and the case.
Enough to know that there are other examples. For instance, you can take the two-dimensional solvable Lie algebra, non-abelian, over in characteristic p, say in x and y, and then factor by y to the p minus y, and that gives you another example. One for each. Yeah. Well, if you fix the prime p, you only get one. But so yeah.
What about dropping the algebraic close condition?
Well, there's more. I shouldn't be telling you. There are other groups, right? I mean, so even at the commutative case. But I think, to be honest, we just haven't done that. I mean, imagine it was quite a good PhD problem, really, to start with a bigger list of commutative guys and see what you can build. Which may be more hard is to drop the global dimension 1, finite global dimension case, because there are definitely other examples there, even over algebraically closed fields of characteristic 0, which are very interesting examples. Infinite. There's at least one infinite class of examples that don't appear on the board that don't have finite global dimension. So that's probably harder.
And what if you drop the prime condition?
Well, yeah, that's interesting. That's kind of speculative, but so if you don't have any condition at all, then it seems to be extremely hard, because then it's quite a major industry to classify finite dimensional Hopf algebras, and you're opening the door to that. But if you just assume semi-prime, so then in the finite case you would be assuming that you knew what every semi-simple Artinian Hopf algebra is, which we don't, but let's pretend we did. Then if you assume that, then every example we know kind of looks like this, that you have your H, and then you have, stopping it being prime down the bottom, you have a finite dimensional. I'm not sure whether to write 1 or 0 here, depends on what you, let's write 0. So this is a finite dimensional semi-simple Hopf algebra. And then the factor by the augmentation ideal of that, the augmentation ideal of K, this is embedded so that the augmentation ideal of K will generate a two-sided ideal of H. Factor by that H bar is should be on our list, if you like. So basically you should get them all by some kind of there's questions about cohomology obviously here, whether this is somehow split or not, but you should get them all somehow by that sort of construction. But that's just conjecture.
Any other questions? Okay, so if not, let's thank the speaker again.